June 1985. At the East Texas Cancer Center in Tyler, a patient lay positioned under the therac 25, a state-of-the-art radiation therapy machine. The technician, Kathy, had seen this routine hundreds of times. Today's patient was here for treatment to remove a tumor. Everything seemed normal. She entered the treatment room, positioned the patient, and returned to the control station separated by a wall. She couldn't see the patient directly, but she had a monitoring system and an intercom. She entered the prescription, electron beam mode, standard dose. But then she noticed a typo. No problem. She quickly hit the up arrow key to edit the command sequence, corrected the mistake, and pressed enter to proceed. The therac 25 began its cycle. Suddenly, the machine displayed malfunctioned 54 and shut down. The display indicated no dose had been administered. Strange, but the machine had been quirky lately with these cryptic error messages. The manual provided no useful information about what the code actually meant. Kathy had seen similar errors before that turned out to be false alarms. The patient was still on the table waiting. She used the intercom. "We had a machine malfunction, but we'll get you treated." She reset the machine and entered the same command sequence again. Same edit, same correction, same enter key. Malfunction 54, again. But this time, the patient had pressed the emergency button and was screaming. When they rushed in, he reported a burning sensation, like someone had poured hot coffee on his shoulder, an intense electric shock running through his body. The technicians were confused. The machine said no dose was delivered. They assumed maybe a muscle spasm or anxiety attack. They sent him home. He died 5 months later from radiation overdose. The therac 25 had delivered approximately 20,000 rads to a concentrated area of his body. A typical therapeutic dose? 200 rads spread across a larger area. The machine had delivered 100 times the intended dose in a space the size of a quarter. It had quite literally cooked his tissue, and this was just the beginning. The therac 25 was manufactured by Atomic Energy of Canada Limited, or AECL, and was considered a breakthrough in radiation therapy technology. Unlike its predecessors, the therac 20 and therac 6, which used heavy hardware safety interlocks, the therac 25 relied primarily on software controls. This made it lighter, more compact, and significantly cheaper to produce. The machine could operate in 2 modes: electron beam mode for shallow tumors, delivering electrons directly, and X-ray mode for deeper tumors, where electrons struck a metal target to produce high-energy X-rays. The difference in power between these modes was enormous. Electron mode. Therapeutic doses measured in hundreds of rads. X-ray mode setup, but with the target removed. A beam so powerful it could deliver tens of thousands of rads in seconds. The older therac 20 had physical hardware interlocks. If you tried to activate the high-power electron beam without the proper shielding target in place, mechanical relays would physically prevent the beam from firing. The therac 25 had removed most of these redundant hardware safeties to cut costs and simplify design. The engineers were confident. Software, they believed, could handle safety just as well as hardware. Software doesn't wear out, doesn't corrode, doesn't mechanically fail. Software is reliable. March 21, 1986. Yakima Valley Memorial Hospital in Washington State. A woman was receiving her 9th treatment for a tumor. The technician entered the treatment commands, another typo. She quickly edited using the up arrow key, corrected it, and hit enter. Within seconds, the patient felt an intense burning sensation, like a blowtorch to her hip. She tried to get up but couldn't move because of the positioning equipment. Malfunction 54 appeared. The machine indicated no dose was given. Over the following days, she lost function in her hip and leg. AECL investigated, ran thousands of test cycles, couldn't reproduce the error. Their conclusion? User error, patient anxiety, impossible for the machine to overdose. She died 3 months later. April 11, 1986, less than a month later. Same hospital, another patient, another routine treatment, another edit to correct a typing mistake. Same up arrow key, same quick correction, same enter. Malfunction 54, same intense burning. This time, the hospital physicist, Frank Borger, was called in. 2 identical incidents, same symptoms, same error message, same editing sequence. He began running controlled experiments, trying to reproduce the exact operator sequence. And then he did it by editing the mode selection rapidly using the up arrow key within a specific timing window. He could trigger malfunction 54 while the machine delivered a catastrophic overdose. He immediately contacted AECL with detailed documentation. This time, they couldn't dismiss it. Let's talk about what was actually happening inside the software. The machine's safety-critical code was written in assembly language, approximately 20,000 lines. The software controlled everything: the turntable positioning that held the X-ray target, the beam intensity, the dose calculation, the safety checks. When the operator entered treatment parameters, the software would read the mode selection and set various flags. If X-ray mode was selected, the software would command the turntable to rotate the heavy metal target into position and enable the high power beam. If electron mode was selected, the turntable would move the target out of the way and a lower power beam would be used. But there was a 1-byte flag variable that tracked the current mode state. This flag could overflow. A 1-byte variable can hold values from 0 to 255. The therac 25 incremented this flag every time the machine went through a setup cycle. If an operator edited the mode selection very quickly, within approximately 8 seconds, using the up arrow key to correct a mistake, the software would enter a race condition. The mode would be changed in one part of the code, but before the corresponding safety checks could update, another part would read the old value. The machine would think it was in electron mode, low power, target out of the way, but the turntable position hadn't actually moved yet. Meanwhile, another section of code would enable the high power setting. The result: high power electron beam, no target in place, direct exposure to the patient. The software did include a check to verify the turntable was in the correct position before enabling the beam, but this check had a flaw. It relied on reading a hardware sensor only once during the startup cycle, not continuously during operation. If the race condition caused the turntable command to be issued but not completed by the time the beam fired, the software would see the last known position and assume everything was fine. The check passed. The beam fired. The patient was cooked. And the malfunction 54 error message was essentially useless. It was a catch-all code that could mean dozens of different things, none clearly documented for operators. The machine's dosimetry system, which was supposed to measure the actual radiation dose, was also unreliable in this scenario. Because the overdose happened so quickly, in less than a second, the dosimetry sensors would saturate and display readings suggesting no dose or very low dose. So operators, seeing malfunction 54 and a dosimetry reading of 0, had no reason to believe the patient had been harmed. By the time AECL fully understood the race condition bug, 6 patients had been confirmed overdosed. 3 died directly from radiation injuries. 3 others suffered severe, debilitating injuries. The investigation revealed multiple systemic failures. First, the software had never been formally reviewed by independent safety experts. AECL had reused code from the therac 20, but the therac 20 had hardware interlocks that compensated for software bugs. When those hardware safeties were removed in the therac 25, the software became the single point of failure. Second, there was no rigorous testing methodology for race conditions or edge cases. Third, the error reporting system was inadequate. Operators couldn't distinguish between a minor glitch and a life-threatening malfunction. The regulatory environment also failed. In the 1980s, software in medical devices wasn't subject to the same scrutiny as hardware. The FDA had no clear guidelines for evaluating software safety. When hospitals reported problems, AECL's initial response was defensive rather than investigative. They assumed their software was correct and blamed operator error. This delay allowed more patients to be injured. What can we learn from this catastrophic failure? First, software is not inherently safer than hardware. Software can fail in ways far more subtle and harder to predict than mechanical failures. A broken relay is obvious. A race condition triggered by specific keystroke timing? That's invisible until it kills someone. Second, redundancy matters. The therac 25 removed hardware interlocks because engineers believed software could do the job alone. This violated defense in depth. You don't rely on a single layer of protection, no matter how confident you are. Third, meaningful error reporting is crucial. If malfunction 54 had instead displayed critical safety fault, beam position, mismatch, do not treat patient, operators would have known to take it seriously. Fourth, testing must include adversarial scenarios. The specific sequence of rapid mode editing was never tested because it wasn't in the normal workflow. But real operators make typos and correct them quickly. That's normal human behavior. Fifth, organizational culture around safety is everything. AECL's initial response was to deny, defend, and deflect. A culture that prioritizes investigating anomalies rigorously could have caught this bug after the first incident instead of the sixth. Finally, regulation must keep pace with technology. The therac 25 helped write those regulations in blood. After the incidents became public, AECL retrofitted existing machines with hardware interlocks and completely rewrote the software with formal safety analysis and independent review. The therac 25 became a textbook case in software engineering, medical device safety, and the dangers of overconfidence in automation. It's taught in universities worldwide as a cautionary tale. When software controls life and death, you don't get to guess. You don't get to cut corners. You don't get to assume. Because the cost of being wrong is measured in human lives. And in this case, the software didn't just fail. It cooked patients alive.